well, but let's see what we can do. No, but okay. So because of this kind of things we do in sister systems, we are exposed to several new things that appear everywhere, and so we are in the robot age, but we are also in the big data age. So big data is also coming, and Richie showed one or some of its consequences. So, but the way I understand this is like something like this: like we have to make sense of huge amount of data, but we cannot understand other than by selecting small conclusions about that. So we, as human beings, try to extract from that small pieces of data that we can analyze and understand and reason upon them. So the idea is that we need things that are proportional to our size in some regards. So we have to understand things that are humane or about the kind of things we can manage because we have big data, but we also have nano physics and things that are beyond our reach. So, but the idea, this beautiful drawing by that most of us are familiar with, is that since ever we have tried to make sense of huge amount of information by building models that are extremely simple, and this illustrates very well that approach, because the man is enclosed in a circumference. So this has somehow to do with, so let's go by parts. It's not working very well. So the center appeared here, like this is by coincidence. The center that Rebecca was referring to is very present in this drawing, and it's not just the center; it's also the radius. I'm sorry, this is not working very well, but you get the idea. And also there is the side. So for me, this is like a perfect representation of how we human beings build models. We take a very complex reality and we try to describe it with some few numbers, some few geometrical or mathematical objects, like a center, a radius, a side, or some few things to find or to discover relationships. We are trying to synthesize a little bit more, not just less data, but data that we can treat symbolically, okay, and calculate that. We need the algebra of things to make sense of things, or the geometry of these things. So okay, but so in this process of now that we have available big data everywhere, we are trying to extract some piece of information from one source or from another. But this is not all we need, because sometimes the data might be very big, but is partially related to what we are doing. It's not. It doesn't point to the core of our problem. Gives us some side or secondary information. Sometimes the data could be misleading because it points in a direction that is close but misses the point. Sometimes the data is fuzzy. Sometimes it's hard to understand. Okay? And sometimes simply doesn't exist at all. So part of the models we try to build, we have to build them from data that can be partially related, that can be misleading, we have to detect that is fuzzy, is not completely certain, or is difficult to understand from our knowledge or to the knowledge we have, or is missing, it doesn't exist because we are modeling something, I don't know, that will happen in the future, for instance. So what the way we try to make sense of this with computers and software is through simulations, okay? So simulations are made from small parts that don't draw very well in this presentation. And these small parts are not the things we want to simulate. A good simulation doesn't define the things we want to simulate. It defines its definitions, its specifications. In Smalltalk, we don't create the objects. We create the classes and the methods, and these will populate the space of objects that will actually do something that is the product of our simulation. So we define things that are maybe smaller because our models are specifications. And these things create... I hate this. I work so hard. This is not Windows.
From full screen to the window.
Ah. So, like this? That's much better. Let's see. Well, it's not so nice. So when we run our simulation, then the specifications create the things that will actually run, and then we have the simulation. So it's an indirection here. And this is the virtual world we create, where the object that we have populated are the actors of our simulation. And what happens here is that we start with a small amount of data. Maybe this small amount of data is the result of many big data out there. But those big data don't go into our specification. There is a selection or a conclusion of that. But when we simulate, we have the chance of create many more objects than specifications, because the logic of the specification, when we populate them, these specifications into actors, we create many things. It's like for modeling a gas, we only have to model one molecule and the behavior, and then we just replicate that and can analyze that. Everybody has seen that squeak thing with the red thing that with collisions infects other molecules. So, and again, this is similar to the experience we have as programmers when we specify the program and then run it. Okay, many more things happen. So that's why for us building simulations is so natural, because that's what we do when we build any kind of application. That's the same process. If you are building a program or an application that simulates something, you can get a lot of inspiration from Smalltalk. Okay. So, but models have parameters. Okay, so in Leonardo's drawing we have the center and the radius and the side. So we have models have parameters, and these parameters are variable. So you can model them as variables. okay? And variables can have many, many properties. We will see some. And the parameters are not constant. They may change on time, some of them at least. And also parameters might be uncertain. You may not know the value of a parameter, but you could know a range around the actual value. And the simulation should help you to better and put the value there. Or just to be aware of the resulting uncertainty, of having uncertainty in the inputs. Also, parameters are mutually dependent, and sometimes you know the dependence. If you are, I don't know, if you have to compute the area of the circle, you will, the dependence is just a formula. But sometimes they are just correlated in some way that you have to discover. So there is, it's very rich. This space of parameters is very rich. Also, some parameters might be unknown, so you have to just put some number and see what happens, or go and find more information. But until you have information, you can still play with your simulation to analyze possibilities or scenarios. And one key is that once you start, if your simulation is complicated, you will end up with many parameters. So, but we don't want that. We want our specifications, our models to be concise. So, but this is a key observation. The parameters' influence is not uniform. Some parameters are more relevant than others. So the idea is to discover which ones and to concentrate on those that really matter. So I will try to show you in how you can do that very in a good way. I will try. Let's see if I can. So, oops. Okay. So here I have a model here. Okay, I will better try to show you the model. So we are in the software industry, petroleum software industry related to petroleum. So the idea is that here the models are about a huge field with reservoirs and wells and facilities and tubes and many other things to extract oil and gas. Okay? So here I have a very simple model with a reservoir. Oops. I didn't know that.
I'm rich.
Don't worry, this is confidential.
Oh, it's a model.
So here we have a reservoir, and I have like two specifications for wells. One well will produce oil, and the other well will inject water to compensate the loss of pressure in the subsurface. Okay, and we have some few facilities here. So this is a representation. We have a well here, a well pad where you connect the well. Then we will process the oil we get here in another facility that does some processing, and part of the water that comes from the well we will reinject into the same well, so we keep the pressure constant. So all the water I get, I inject there. Very, very simple thing. So here we have several parameters, like the amount of oil that is in the surface, the subsurface, like oil in place. Okay? Here there is some number. This number is not certain. We cannot be certain about that. Okay? So we attach a probability distribution around that. Okay? This is how we model uncertainties with probability distributions. So there are several parameters, and there are few that matters, like the oil in place or the amount of reserves that one well could extract from that reservoir, and some costs, like for instance, the capital expenditure I had to spend in order to build the well pad that to connect the wells in the surface, and how long it would take to build all those tubings and everything. And again, these are uncertain parameters, and they are correlated. That's why we have here some additional mark. But because the longer it takes, the more expensive. So we have some parameters, cost and oil, and we are trying to understand how this will work. But of course, we don't want to produce only one or to drill only one well. This is just a prototype. This is the spec. We want the reservoir to automatically develop itself. So we will populate all the reservoir with many wells that will copy the characteristics of. So this is all about our application. But I think it's a valid example of a model and a simulation. So here is the result of running the simulation many times with what is called sensitivity analysis. Sensitivity analysis is you take some of the uncertain parameters, or all of them, and you start modifying them a little bit, one by one, and then measure the impact that would have on the output. Here the output is money, okay? And money is measured with financial mathematics, NPV, net present value, money brought to the present, okay? So here, if you, and the number here next to the NPV calculation is the discount rate. So if you go with no discount rate here, you can see the impact on NPV when you modify the well reserves a little bit in several parts of the range, and then you have the oil in place, etc., etc. So here the well reserves is one thing, the oil in place is another. So what you can see that there are many others that don't really matter. So you don't have to waste time on them. But be aware that if you change some other parameters, then the impact may be very different. And I don't have time to go into detail with this, but for instance here, capex is the second most important parameter, that here is like the 4. So many things could change. So you need a simulation to understand all the consequences of these uncertainties. Okay. So let's try to continue with this. So, okay. So this is the sensitivity analysis here, and the conclusion is that models mostly depend on few parameters, and sensitivity analysis is the tool to detect them. So you concentrate there. And as I said before, probabilities are the instrument to make sense of uncertainties. And so you as programmers, no matter what topic or subject or field are you working, you must understand probability distributions. This is mandatory. Big data is coming, and it's not that hard. Don't be intimidated. It's not that hard. And it's very easy, it's very powerful. So usually you have two curves, the density curve and the cumulative one. So this is just like lesson number 1 if you are not very familiar with probability distribution. So the idea is that these, like the circle and the square, are mostly described and defined with few parameters. So here is the mean value and the standard deviation. These are just two numbers that define all the curves. And this is a characteristic of probability distributions. Probability distributions have very nice probabilities. You define them with very small data, just a couple of parameters. The normal distributions, 2, mean and standard deviation. The log normal the same, Bernoulli only 1, etc. All the popular, well-known, named probability distributions, you only need 1 or 2 numbers for them. So you define with small data. You can refine. You start with a probability distribution, and then you refine that as you learn. So you start like this, with an initial parameters, then you somehow get new evidence, and then you update the parameters and start over. And this process is very well formulated in mathematics, is learning. I'm using learning here in a very technical way, like Bayesian learning. There are algorithms to apply this. So learning is very important, and you can embed learning into your model. It's not that you learn, your model learns. That's very powerful. The other thing is that probability distributions can be correlated. You can define not very well defined dependencies between variables. One to many, many to many, one to one. It's up to you. And they generate a continuum. They are more than big data. Big data can be huge. Yesterday or today, I'm also lost with the days, Richie showed numbers that he couldn't read. But this is way more. This is a continuum of possibilities. Because from this curve, you generate, like just doing this process, random numbers that follow that kind of distribution. So you can generate 1, 2, 3, a million, or whatever the crazy number you want. So this is very powerful. And so the idea of this, the last 4 slides, is that you define, you refine, you correlate, and you generate. And you have something that generates not big, but a continuum range of possibilities. So there is nothing you cannot explore. So you build the model or the simulation. You concentrate on the few parameters that really matter, even you have to define all of them, and you extract from this one key output parameter, the amount of money you're going to do, or whatever. Okay? So now, but these numbers, the inputs are not just a number, are a distribution, so they belong to a range. So you have to try with many, many samples. So you repeat the same pattern, and at every iteration you put as input a new sample of the variable. So you repeat this as many times as you can, usually thousands of times. And you get thousands of outputs. And then you take these outputs and calculate some statistical estimators, like the mean value, the average, and the standard deviation of the output. So in this way, you can measure the impact of your uncertainty in the input on the output. You can see if your model amplifies or reduces or maintains the level of uncertainty on the qualities that you are interested in learning. And you can repeat this at the same time for many, many other outputs, because complex models don't have just one output, they have many, okay? And you can do all of this at the same time. How? By running the simulation many, many times. So the idea is that when you build a simulation, you amplify somehow your understanding, because you populate a small set of specifications into a virtual world of possibilities. So this is you amplify what you have. But also we have seen that with probability distributions, there is another dimension for amplifying this, the knowledge that your model captures. So when you combine both, you have like simulated big data of any size, okay? And this is very powerful. Now, it's also very costly. It's also very costly in terms of computation and power. And we in Smalltalk usually run on one thread, so of the processor. So, is Smalltalk really useful for this scenario, for doing this? Because the theory is excellent. We can model a lot. We can understand. We can define the probability distributions, make sense of everything. But how we use our Smalltalk with one thread to compute this in an amount of time that is all, again, of human size. Given that we have to repeat this thousands of times. Well, the good news is that these things you can run them in parallel. So you can run them in parallel in several machines or in your machine with several cores. So let's think for a moment that we have several cores. So we can run with some samples, the entire space of samples, I can divide them by the number of cores I have. So I can, if I have, I don't know, n cores, then I can run these things in parallel. So in parallel, they will run as if I had many threads, even though I have only one, and I just instantiate my simulation in another process. Okay, so the problem now we have to solve is how to control all these processes that are running in parallel. But we have all the tools in Smalltalk, because in Smalltalk we have processes. Okay? So one Smalltalk process can connect to an external process that runs in one core, one of the cores. And we already have that in Smalltalk. And we have process scheduling as well. We already have that, and we are familiar with that. If we are not, we can understand that completely, because it's all written in Smalltalk. And we have semaphores for coordination. And we have timers, and we have delays. Okay? And we have also a language for dealing with these objects. We have signal, wait, critical, fork. All these things have been in Smalltalk from the very beginning. So you don't have to add anything to Smalltalk. You have just to use the things you already have. And so you will need to do something for parallel enumeration. So do like parallel do or something like that. I will mention something like this in a minute. And you also will need to communicate between processes that are external to your instance of Smalltalk. And so you will have to choose a channel that could be sockets, pipes, messages, I don't know, files, virtual files, whatever you want. And everybody here has experience with at least one of these things. So it's perfectly possible to connect the processes. And you will need to send objects over these channels. So you will need serialization. We already have that, okay? And you will need events to be aware when something finished or is about to start, or you had an error or whatever. Again, it's something we are all used to. So the only thing that I find interesting is that two things. One, debugging. Debugging works very well, except that you need logging. Okay, you have to log a lot of things into. Maybe there is a better solution. This is like an open problem. We use logging for debugging multiple processes. Another thing is you need something for parallel enumeration, like run. So I have several machines. Every machine is a process in running on a core, on a remote machine. So machines parallel do run. Okay, this is the controller. So you need some parallel do mechanism. So the idea for the parallel do is that after this message is sent, I don't want to proceed with the next message until all of this is finished. Okay? So just fork is not enough. So how do you build this parallel do? How do you implement this? Well, you create, so you can read this with detail. You create a new semaphore. Now you send the do message with no wait. You just evaluate the block. And when the block is evaluated, you signal the semaphore. And at the end, you wait the number of times you evaluated the block. So this will continue only when the number of signals matches the total numbers of elements in the iteration. And the no-wait block is just a fork. Okay? This is very simple and gives you a parallel enumeration that when everybody finished, you proceed with the next small talk sentence. Okay? And I don't have more time, so let's finish here.
Maybe when you're working processing XPM, you get the responses and control the letter of the end because of the thread.
Yes, very good question. No, the idea is that the external process that you somehow launch it, there are many of them, you represent here with a process that does nothing but wait for this to, I don't know, send an event. So what you fork is this process that is a representative of the actual one that is doing all the work. But you represent this here. Thanks for the question. Sorry? Other, yeah.
So this is, I think this is really, so,
Sorry, but you're out of time.
well, okay, well, I will ask that one.
Quick.
So, what are you, let me ask myself,
Boris, please concentrate. Make the question.
So,
You can do it.
we have, even though we do not have a multi-threaded VM, here we are introducing into the language the fundamental ability to express parallelization into small talk.
Yeah.
So that at such time that we have a VM that can
Yes.
utilize 100%, like 104 on a Clara chip, or that chip, that we will not need to change the program.
Yes.
So this is already like semantic intention, new language. We already fundamentally have that.
Yeah. That was a bit smart. No, está bien, se hace muy tarde.
El problema es que yo me tengo que ir al aeropuerto.